Okay, so we kind of ran through the periodic table up and down and decided there was this hidden value called Z effective, which was the effective nuclear charge that is felt, so that's the attraction felt by the valence electrons to the nucleus. And it turns out to be very, very revealing. It showed us an increase as we moved from left to right. So Z effective increases from left to right, and that's going to explain a couple of things. That explains a contraction in radii, and it explains an increase in ionization energy. Ionization energy being the energy required. Did they lock the room up?
No, I think I lost it.
Do you need a writing utensil of some description?
Yeah.
Does anybody else have a spare pencil? There you go. So, as Z effective increases left to right, that's the increase in attraction from the valency to the nucleus of the atom. That's going to make our atoms smaller, and it's going to make the electrons harder to pull off the atom. So we go from being metallic behavior on the left, where everything is easy to ionize, to non-metallic behavior on the right, where stuff is difficult to work with. Okay? As you move down a group, Z effective doesn't really do much. There isn't a significant change in top to bottom, and any effect that we're looking at is overridden, if that's a word. I know it's a word, I don't know if that's how you spell it, but I'm spelling it today. Overridden by massive increase in size. So the trends down the group are going to be because of the new quantum shell. And n is our principal quantum number, lowercase n. It is also the number of the period. So you go from period 1, it only contains s electrons. Period 2 contains the 2s and the 2p, which are bigger, more voluminous than the 1s orbitals. And then you move down into the 3, where you have s's and p's. And technically you have d's as well, but the d's don't show up until the 4th period because of an anomaly. Okay? So that's where we are. Let's go ahead and plot something. If I were to plot ionization energy against Z. Now Z is my nuclear charge, but it's also my atomic number. Right? Z is just the atomic number. There are no atoms that have an atomic number of 0. But there is an atom that has an atomic number of 1, and there is an atom that has an atomic number of 2, and there is an atom that has an atomic number of 3 and 4. So this is period 1. And here's 3 and 4, that is lithium and beryllium in period 2, 5, 6, 7, 8, 9, and 10. And that takes me to neon. Ooh. You just came from physics. Yeah. What's an electron volt? Yeah. It's a unit, and we measure some energies in electron volts. Most energies in chemistry are then translated into kilojoules. So I'm not going to put a value. I'll give you some values for this, but oh, actually, I've got them in kilojoules. That's crazy. The book shows the table in electron volts, and then a graph in electron volts, but then the table is in kilojoules per mole. Where am I actually going to go? So somewhere between. There you go. We're going to pretend. This is a little descriptive table. It's not, we're not doing anything quantitative. So this is ionization energy in kilojoules per mole. Okay. It takes about 1,300 kilojoules per mole. That's quite a bit to remove. So ionization energy is this. In the gas phase. That's your ionization energy. The energy required to remove an electron. Okay. Hydrogen is 1s1. Helium is 1s2. Are we expecting helium to do this thing easier or harder than hydrogen just did?
Way harder.
Like twice as hard. 2,300. Hydrogen is in group 1, left-hand side of the periodic table. Helium, group 8, right-hand side of the periodic table. Things on the left do this easily. Things on the right don't. Okay. We're going to finish that quantum shell and then come back and look at lithium. Lithium. Can we predict where lithium's going to be on this scale? Anybody want to hazard a guess? And it would only be a guess. What about that? In fact, we really should go up to 11. This one goes to 11. Because 11 will give us sodium. All right. What about beryllium? Should beryllium be easier to oxidize? Should it undergo the ionization energy easier, or should it undergo it more difficultly? Think about what you're doing on the periodic table. You're moving from left to right. Is this going to get easier, or is it going to get harder? It's going to get harder. And lithium is 513. Beryllium is here. And then boron. So I want to make sure that I'm doing this right. trend, but that trend takes a little hiccup. Little hiccup. And then carbon is about 1100. Carbon's on 6. So we're here. And then nitrogen is about 1400. And then oxygen's 1300. All right, so perhaps this is all within the realm of experimental error or something like that, but I don't think so. I think there's something else going on here. And then fluorine is about 1700 and neon is 21. So I have a trend line. And my trend line does that. Because these two data points are not part of this data. Because that's the end of the first period. Now, if I want to include them, I could draw a line that goes between the whole thing. But there is this right here is a trend. And these two lines, these two dots do not appear to be on it. Although, it's really this one that's off the dot, off the line. This is much more of a line. And remember, I'm just doing this on paper. Than that one. So this one is high. As is that one. That one's a bit high. But that nitrogen's sticking out. It's off the trend, and we need to know why. So we're going to come back and do some more general chemistry. This is not anything that you've not seen before. And explain why the trend across a period isn't completely linear. Anybody got a clue? Okay, good, doesn't matter, because we'll get to it. Before we do, number 11 is sodium. Where do you suspect sodium is on this chart?
Does it go back down?
It does go all the way back down. If this is lithium, where do you suspect sodium is?
A little bit higher.
A little bit higher. Does that make sense? I wouldn't write it down. I'm only repeating what somebody in the room said.
Oh.
Why would you say it was a little bit higher?
Just could
Yeah,
That makes
well, I mean,
sense.
it's got more stuff in it. Bit lower. This is revealing something to us that we knew by observation, that as you move down a group, your metals become more metallic. Lithium is the top metal in group 1. If we ignore the fact, let's go all the way to the top of group 1, hydrogen. There are people out there who think that hydrogen should belong in group 7. That's complete nonsense. But It doesn't obviously display metallic behavior. It is a metal. You just have to get it down to liquid helium temperatures or lower. You have to get it really, really super cold before it starts to demonstrate any of the behavior that would make you think that it could be a metal. Lithium's a metal, but sodium is more of a metal than lithium is. It does all the things that make you be a metal, but it does it, all its reactions, better, faster. And potassium does them better and faster too. In fact, so good, so fast that that's now dangerous to handle. Rubidium, more so. And then by the time we get down to cesium, nobody touches cesium. That's just now so very, very good at doing this behavior that it's incredibly difficult to handle. Okay, so trend down the group. Atoms get more metallic. And then across the period, Z effective increases from left to right, but there is a glitch. There's a glitch in the data. And where is that glitch? Well, in period 2, that glitch is at nitrogen. In period 3, there would be a glitch at phosphorus. In period 4, there's more than one. And we'll talk about that much later. All right, so I need to explain this. All right, who remembers anything at all about quantum numbers? Good, we'll do it again. I mean, if you all were completely 100% familiar with them, we would just go as it is. There's a gap in your education, and I'm about to fill it. Anybody know how many quantum numbers there are? Anybody know what quantum numbers do? Who taught you general chemistry? It was before I was here. Okay. Well, maybe she did and you just don't remember. What quantum numbers do is they describe the environment and the behavior of an electron. And any electron can be described by 4 quantum numbers. Do you remember Aufbau? Do you remember Hund's rule?
That one sounds familiar.
Do you remember Pauli's exclusion principle?
That also sounds familiar.
So, quantum numbers, there are 4 of them, and they can describe any electron. And so what we're saying here is no 2 electrons can have all 4 quantum numbers be the same. Quantum number 1 is n. N is the principal quantum number. And it describes size, it also is equal to the period number on the periodic table. Let me just check, because once upon a time, the quantum numbers were N, L, M, and S. Then they changed that, and I don't know why, because they didn't make it better. If you're going to change things, you need to improve them. They changed it to N, L, M subscript L, and then M subscript S. And I want to make sure if the book has quantum numbers, it may not even have them, that I give you the same set that the book does. Does it have quantum numbers? Check for the, check in the glossary. Don't want to go down this path and then find out I'm doing it slightly differently. PP quantum numbers, number 9, page 9. Oh, here we go. It says formally something or other. Principal quantum number, N, orbital angular, L, formerly called the azimuthal quantum number. I wanted to know that because I almost wrote that down. And then they go with M subscript L, and I'm assuming on the next page they must go with M subscript S. They never really get around to it. Okay. L is now called the angular momentum quantum number. Used to be called azimuthal, because an azimuth is, I'm not sure if I can really explain what an azimuth is, but things like gyroscopes, you know what a gyroscope is? It's like the spinning top. That has an azimuth. It's like the angle that's, I think it means the angle at which something rotates. That's the angular momentum quantum number, L. Now, here's the deal. N, because it's the period's number, has values that N can be 1 or 2 or 3. What values can N be? 1, 2, 3. 4, 5, 6.
7.
Ooh, we haven't found any of the atoms in period 8 yet. Whole numbers, all positive, currently from 1 to 7. We're not into period 8 yet. It's going to be a while before we can get there. All right. What L represents is shape. What it's really telling us is that L, the value of L, is the number of nodes in the orbital. Do you know what a node is? What's a node?
It's like the intersection of like 2 lobes, right?
It's when your value goes to 0. Now, L can have values. L has whole number values that are somewhere between n how am I going to say this? It's between 0. There you go. That would be easy. Whole number values from 0 to n. Whole numbers. Sciencey way of saying whole numbers, integer, right? Are we all okay with the word integer? An integer is a whole number. So L has whole number values between 0 and n. That's right. It better be right. All right. Now, what used to be called M is now called M subscript L. And this is the, oh, it's not the magnetic yet. I'm going to call this magnetic quantum number. Yeah. We're changing the names on them. And what M does is, I think there's going to be an n minus 1 up there in a minute. I think I'm going to change that. M subscript L, there's no parentheses there, M subscript L has values that are minus L through 0 and then out to plus L, all in steps that are integers. It'll make sense when we put numbers in here. It will all make sense. And then the spin quantum number, this is our last one. This used to be called S, is now called M subscript S. M subscript S is either minus 1/2 or plus 1/2. Okay, when n equals 1, the value of I have a mistake on the board and I know it. That n is n minus 1. I'm not going to say it, but it is. I'm not going to lay it out that way. Because there's no other way to do it. So this, yeah. Okay. All right, let's put some numbers in this. When n equals 1, you're in the first period. N equals 1. What are the allowed values of L? L can be any number between 0 and n minus 1.
0.
So there's only one allowable value. L equals 0. When L equals 0, you are an s orbital. L equals 0, represents an s orbital. M subscript L has values of L as a negative number all the way through 0, all the way out to here. This gives me my number of permutations. There's only one of them, and it's going to have this number here. And then M subscript S is minus a half or plus a half, and that tells me that I have 2 electrons. With opposing spin. Aufbau, when you learned electron configuration, Aufbau said start at the beginning. Put the electrons in the 1s before you move them into the 2s. Put them in the 2s before you put them in the 2p. Fill the 2p before you start putting them in the 3s. That was Aufbau, building up. That was then followed by Hund's rule that says if there are degenerate orbitals, meaning have the same energy, like the p orbitals, put them into individual orbitals before you pair them up. And then Pauli's exclusion principle that says if you must put 2 electrons into the same orbital, they must have opposing spin. Does that sound familiar? I'll write those rules out later. Pauli's exclusion principle says if 2 electrons are in the same orbital, they must have opposing spin, and my spin quantum number tells me that the electron spin is plus half up, plus a half down. That's what happens in period 1. All I have in period 1 is 2 electrons. They're in a spherical orbital, and the quantum numbers distributed that for me. Now, when n equals 2 in the second period, L is any number, any whole number between 0 and n minus 1.
So 0 or 1.
So either 0 or it's 1. So L could be 0, which is an s orbital, or it could be 1, which is a p orbital. Let's look at what happens for L equals 1. When L equals 1 instead of 0, we know what happens when L is 0, ML is 0, and the MS is plus a half or minus a half. We know that already. Let's look at what happens when L is 1. When L is 1, M subscript L can have any value, as long as it's a whole number, between negative L through 0 up to positive L. And because L is 1, my values for M are minus 1, 0, and plus 1. So that's a p orbital. And it's in period 2. How many atoms are in the p block? How many atoms in the p block? You can look at the periodic table. No, just across, just
Oh.
groups. How many groups in the p block?
6.
6. 2 electrons per orbital. That means I need 3 orbitals. Do we know the names of the p orbitals in the second period? We will today. I have an X and a Y and a Z. An X and a Y and a Z. X and a Y and a Z. I have 3 dimensions. P orbitals are the shapes of figure 8s on dumbbells. There's one. This is called the 2px. That's an uppercase 2, if there is such a thing as an uppercase 2. It's a regular 2, a lowercase p, and then a subscripted x. These bulbs, these lobes for the shape of an orbital, what do you think they represent?
Where that electron would be, like in the probability.
It's the probability of finding the electron. It's something that we call electron density, and an s orbital is just a sphere. I should have done that in red. It's just a sphere. How many times in this sphere does the electron density go to 0? None. Never. The sphere does not have any nodes. Its value does not go down to 0. See that right there, the nucleus? What are the chances of you finding the electron at the nucleus? 0. There are no electrons in the nucleus. The cloud of electrons can be around the nucleus, but cannot be at the nucleus. It's where the protons and the neutrons are. The electrons don't belong there. You can never find the electron at the nucleus. It has a node. The probability density of you finding the electron at the nucleus goes to 0. I have a node, just the one of them. That's my number of nodes. This is called the 2py. Guess what that one's called?
Easy.
That's the 2pz. I'm afraid you were all wrong. So I have 3 probabilities. What the magnetic quantum number tells me here is the number of permutations. P orbitals hold 6 electrons, but you can only hold 2 electrons per orbital. Therefore, I need 3 p orbitals. And they can't all be in the same space because electrons repel each other. So if I sum those up, it's approximately spherical. It's approximately spherical. each of these will hold 2 electrons, and each of them will have magnetic spin numbers of either minus a half, plus a half, minus a half, plus a half. 6 electrons in 3 orbitals, each with 1 lobe, all in the second period. Quantum numbers just break down and tell you what it is that you're expecting and how many of them there are going to be. Okay, now, what happens when you get to the third period is we start the next type of orbital. When n equals 3, L could be 0, that's an S. It could be 1, that's a P, or it could be 2. And when L equals 2, you're a D. You're a D orbital. Let's have a quick look at the D block. Count how many atoms wide the D block is. 10. I need 10 electrons to sit in these D orbitals. Okay? So whatever I write down on the board needs to back that up. So when L equals 2, that means that M subscript L has what values? It's erased from the board now, you can't look at it.
You mean
Minus 2,
0, 0, negative
minus 1,
0, negative 2.
0, plus 1, use the sign, and plus 2. Don't just say 1 and 2. Make sure that it's a plus or a negative. So I have 5 permutations. That's 5 orbitals. And each of those orbitals can hold 2 electrons. And therefore, there's my 10 electrons. L is the number of nodes. So each of my D orbitals must have 2 nodes. You know the shapes of the D orbitals? Well, no, if you didn't know the shapes of the P orbitals, then yeah, you'd not be showing this. But I teach this in Gen Chem. I should have done it. Doesn't matter. Listen, we are going to teach you the best inorganic chemistry that we possibly can. It's just going to take a little while to get there, but when we get there, everybody's going to know the same amount of stuff. There's no point in me rushing into coordination compounds of cobalt and realizing nobody knows how to count electrons. Okay, so. D orbitals, so S orbitals are spherical. D orbitals are figure 8s or dumbbells. 2 B's in dumbbell or just the one? I think it's just the one. Dumbbell? I think so. And D orbitals are cloverleafs. The quadrifolio type, the 4-leaf. All right. This is going to take some practice. Everybody write their axes so that I can keep everybody on track at the same time, because you do not want to not pay attention to what it is that I'm doing. This is not a competition, but if it were, Peyton, you'd be last.
Make sure that it looks pretty.
I know. Well, see, and that will pay dividends later. All right. I'm going to do 2 sets of p orbitals on top of each other. It's like a clover leaf. But here's the trick. The lobe sits between the x and the y. It never touches the x or the y. This is called 3D X, Y. Between the axes. Okay. And my next one is going to be called 3DXZ. That means that the lobes sit between the X and the Z. They don't touch it. So they go here. Z is my, so in X and Y, you know, you've got X and Y. When we make that 3-dimensional, this X, Y, and Z, we normally tilt the Z to be upwards. In all branches of chemistry, what the Z-axis is arbitrary, except for inorganic chemistry. There's going to be a time when we see a metal and another metal decide, I'm interested in making a bond to you. And when they make that bond, it's down the Z-axis. So we are going to keep track of this. And when we write it, it is actually going to be horizontal later on. But it's normal to write the Z right here, vertical. Between the X and the Z. And between the X and the Z. And between the X and the Z. So I've got a flat one, and I've got one that's standing up. And now I'm going to have one that goes at an angle. Because my next one is 3DYZ. That is between the Y and the Z. Flat, standing up, at an angle. These three do not sit on any of the axes, and these 3 d orbitals are what we call non-axial electronic orbitals. Now I'm going to have a cloverleaf that sits entirely on the X and the Y axis. And this is called the 3D x squared minus y squared. I did see this explained quite nicely one time. I remember an inorganic professor of mine actually went out of the way and said, oh, no, let's solve that. And we kind of solved it mathematically, and turned out, because the one that follows is a little bit odd, follows that it doesn't really matter which axis you call x and y. And if they're empty, they're all the same energy. That leaves me one. And the one remaining looks like this. It's like a big p orbital with the life preserver, with the donor. And this is called the 3D z squared. And these two have all of their electron density on the axes, and these two are axial. And when you start putting electrons into d orbitals, whether they are in axial or non-axial orbitals, actually makes a difference and will dictate what the shape of the material that you're making turns out to be. It's really, really cool. It's one of the coolest things that I've ever seen in science, in chemistry. And we'll, before the term is out, we'll describe it. We're going to start putting electrons into our transition metals, and there'll come a time when it will change shape. And it will change shape predictably to stop repulsions between electrons in itself or with something coming into bond with it. And when they change shape, they change color. And so that's an added bonus. Okay, now that's where I stop in general chemistry. In 1341, I do that in 1341. This is a 3000 level class, so let's do the actual difficult part. When n equals 4, when n equals 4, we get to the ones that I can't draw. When n equals 4, we're in period 4, technically. Our L could be 0. It could be 1. It could be 2. Or it could be 3. What happens when L equals 3? You make F orbitals. Okay. So the values of ML when L equals 3, don't write N anymore. When L equals 3, the values of ML are -3, -2, -1, 0, +1, +2, and +3. That is 7 orbitals. Each can hold a maximum of 2 electrons. That's 14 electrons. Look at the F block on the periodic table. Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, prusium, holmium, erbium, samarium. That's not yttrium, and then lutetium. What's YB?
Eubidium.
No. Eutubium.
Not just.
Is that ytterbium? Yeah, that's ytterbium. 2, 4,
Yeah.
6, 8, 10, 12. $14. Now of that, is that actually showing me 15? Because if it is, then the lanthanum actually, it is, isn't it?
Mm-hmm.
So, it's showing me 15. Do you know why it's showing me 15? Because there's clearly 14 of them.
The Lathian's part of the D.
Yeah, the first, number 57, if you look, we jump, it's saying here, one of them is double dipping, lanthanum, double dipping. 14 electrons, it needs 7 orbitals. And each of those orbitals, oh look, 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 look. 2 nodes. Can we see the nodes? The time where the electron density goes to 0, it's got one that way, and it's got one that way. There's my node. All right, the F orbitals. I can't draw I never learned to draw the F orbitals. I might be able to recognize them. Oh, they are things of beauty. Wow. They're on page 15 of this book. And yeah, I am not going to attempt to draw those. They're like d orbitals that have then been sliced. It's like if the d orbitals were made out of marshmallow and then you just like slice them. So now I've got 2 sets of everything. So I've got an additional node that has cut through what was my d and like has just doubled the electron density of everything. Okay? If you were to put all of those together, which one did I not do? That one, that one, that one, that one, and then this one, and then that one. It's approximately a sphere. Okay. By the time that the F's get a look, I've already got the S around, and then I've got the P's around it. And now I've put the D's, and they have larger penetration. They've got longer orbital penetration. So now I've got the D's. Where are the F's going to go? The F's kind of sit in these little double lobes outside of everywhere. And they are tricky to draw. I never learned to draw them.
So we don't.
That's what it sounds like. Names. I don't even know the names of the F orbitals. The names of the F orbitals are things like x cubed minus z squared, y cubed minus yx squared. Yeah, they're tricky. All right, each of these has an m plus half, ms that is plus half and minus a half, spin half for each of those. All right. So we know shapes, and we know why. Let's look at configuration. And why are we doing all of this? We're doing all of this to answer one dumb question. Why is nitrogen not on the line? Okay? Nitrogen needs to be on that line, and it's not. And in order to get there, I had to show you quantum numbers can describe any electrons. Every electron is unique, and the quantum numbers describe the shapes of the shapes and multiplicity, number of permutations of the orbitals. Okay, so now I have the orbitals, I can start putting electrons in them. And I have 3 rules for electron configuration. And the first is Aufbau. Anybody speak German? It sounds German, doesn't it? It's I want to shout. German's a shouting language. Aufbau! This is the building, it's actually building out. Translates in English to building up, but it really should be building out principle. And what this means is it says fill the 1s orbital before the 2s before the 2p, etc. Okay, so we are going to go sequentially. 1s, 2s, 2p, 3s, 3p. Okay, that's got me all the way through the third period. Now in the fourth period, potassium and calcium, they're in the 4s. What about scandium? Where are its electrons?
3D.
They're in that, those are d orbitals. And the d orbitals were predicted by the quantum numbers to be in period 3. They didn't show up in period 3, but they belong to period 3. Technically, they really are in period 3, but the 4s is lower in energy and jumps ahead, because s orbitals are spherical. Spheres arise in nature because they are the most perfect way of holding volume. That is the best amount of volume with the smallest amount of surface area. So the S's are more efficient at holding electrons, and the 4S's jumped out into the 3 before the 3D, and then after the 3D comes the 4P. Okay, so some people point at this and say it comes out of sequence. Technically, that one does. These two are out of sequence. So what I'm going to do is I'm going to fill this first. Not first, but before the 3D. The 4S gets filled before the 3D. Now, tell me one thing that metals do.
They oxidize.
Yes. And oxidation is what?
Ionization.
The loss of electrons. Oxidation is the loss of electrons. If I'm looking at a transition metal and I'm going to lose electrons from that transition metal and make the ion of that metal, before I touch these D electrons, I remove these S electrons. They go in first and they come out first. Okay. That's outbound. Then we have Pauli's exclusion principle that says if there are two electrons in an orbital, they must be spin opposed. that means that the ms of one equals minus a half, and the ms of the other equals plus 1/2. And then there is Hund's rule. And Hund's rule is for situations in which we find ourselves with orbitals that have the same energy. And the word for same energy is degenerate. So if I have a series of orbitals like the 3D or the 3p or the 2p, for degenerate orbitals, put individual electrons into available empty orbitals before pairing them up. There is a kind of energy disadvantage, disincentive to pairing electrons. Electrons repel each other. They don't want to be in the same orbital. They would rather be in individual orbitals. So for general available empty orbitals before pairing them up. Okay. Did you do the little boxes where you put the electrons in them? All right, good. Let's do that. Let's do carbon, nitrogen, oxygen, and fluorine. Carbon is 1s2, 2s2, 2p2. And so the little boxes work my way through. Carbon has 6 electrons. It is in position 6 on the periodic table, means it has 6 protons, therefore it has to have 6 electrons, and they go this way. 1. And our symbol for an electron is an arrow with a single barb. That's hydrogen, that's helium. 2 electrons in the same box must obey Pauli's exclusion principle. Then Aufbau says, my next electron has to go in the 2s, cannot jump up to the 2p, has to go in the order closest to the nucleus. So this is starting from the nucleus and spreading outwards, the building out principle. 2s2. And then that leaves me 2 remaining electrons. And this is where Hund's rule comes in. It says my next electron has a choice. It could go here, or it could go there. Aufbau from here to here to here. Pauli's exclusion principle inside the box. Hund's rule inside this block. Nitrogen, 1, 2, 3, 4, 5, 6, 7. Oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Oh, and back to Pauli's exclusion principle. One, 2, 3, 4, 5, 6, 7, 8. I have just explained why nitrogen is not on the line. For nitrogen, I have one electron in the 2px. I have one electron in the 2py, and I have one electron in the 2pz. These are all at 90 degrees to one another. And there's a node at the center. This electron could not interfere with that electron any less than it currently is. And this electron could not interfere with that one any less than it currently is. They're at 90 degrees to each other. So this electron gets a good look at the nucleus, as does this one, as does that one. By the time you become oxygen, I have to pair that up. This is now getting in the way of my other electron. So at nitrogen, each of these electrons, because of the shapes of the orbital and the configuration and the number of permutations, those electrons are held a little bit tighter. A little bit tighter than oxygen was or the carbon was. And this one is off the line, more difficult to remove. Okay. We call those 90-degree sets orthogonal. No worry. No worry. Yes. You're done. I posed the problem, I solved the problem. Go home. You don't have to go home. Can't stay here. All right, what's next? What's next? We might actually move ahead in the book. Oh, I know what we're going to do. We're going to do, oh, you're going to love what's next. Yeah. Molecular orbital theory. That's what's next. Because all we've just shown you atomic orbitals. Now we're going to linearly combine atomic orbitals to make molecular orbitals. And molecular orbitals are fun.